this particular course is on port and harbour structures. The main important requirement for building a port is environmental management. You cannot build the port wherever you want to build a port. There are certain locations where we can build the port without a breakwater, but most of the locations you have to build a breakwater. So in this particular slide you are seeing a breakwater here. This is called as the south breakwater and this is the north breakwater. This is for a fishing harbour in Pondicherry. So once you construct the breakwater like this, you have accretion on the southern side of south breakwater and erosion on the northern side of the north breakwater, but you are not seeing all these things here in this slide because we have done what is known as artificial nourishment. This we will explain as one of the method for environmental management. Generally when you build a breakwater like this into the sea, it obstructs the flow of sediments which naturally takes place. This sediment movement is from south to north on the east coast. So when the sediment is trying to move from south to north, because of the construction of the breakwater there is a deposition on the southern side, this is called as accretion. There is erosion on the northern side, that is called as the erosion. The original shoreline was somewhere here and you have so much of accretion on the southern side and so much of erosion on the northern side. This erosion has taken place right up to this end, somewhere here and about this building also where they have put the stones. I think you are able to see the stones because the erosion has taken place up to this end. By doing artificial nourishment, by taking the sand from inside the harbour basin, we have advanced the shoreline up to this point. This is one of the methods which can be used for environmental management. So in this lecture we will discuss what are the causes for erosion and how to manage this erosion. What are the causes for erosion? Mostly these erosions take place during storms. Storms or cyclones, they are experienced in the east coast, both southwest and northeast monsoon. For Tamil Nadu coast the southwest monsoon is not predominant, only northeast monsoon is predominant. So we have 3 seasons, one is called as southwest monsoon, another is northeast monsoon, next one is non-monsoon. So the southwest monsoon we can say from March to July, this one we can start from October middle to December middle, that is December 15th. The other seasons we can classify as non-monsoon. The littoral current from southwest monsoon, suppose you take this as the north, the movement in the southwest monsoon is from the south to the north. In the northeast monsoon it is from north to the south. That means if you build a breakwater, in one season there will be the deposition on the southern side, whereas in the other season the deposition on the northern side. In non-monsoon the deposition will not be very much. Okay. Approximately the Pondicherry harbour, what I have told, the sand which is moving is about 1500 cubic meter per day on average, and it is maximum in Paradip port, there it is about 1.5 million cubic meter per annum. This coastal erosion generally takes place during storms and cyclones. And there are many other causes, both natural and man induced. The man induced is the construction of breakwater. Natural causes are those which occur as a result of response of the beach to the effects of nature. Nature effect may be the concentration of energy in the coastline, that depends on the bathymetry. There can be some headlands, so it is a coastal feature, it is called as a coastal geomorphology. Man induced, many reasons are there. One of the thing which we want to discuss is construction of breakwater on the natural system. So we will list the various natural causes. One is the sea level rise. They say the sea level is rising, it varies from 1 millimeter to 100 millimeter, that is the range they are telling per annum, it is not yet quantified. The variability in sediment supply to the littoral zone, the sediment is coming from the rivers. When there is a sediment is there are various sources, one of the sources the sediment coming during floods from the river. Storm waves, so when the wave is higher, that is the wave height is more, what it does is it carries more sediments and then creates erosion. Then we have wave and surge overwash. Surge means when the cyclone is crossing, there is a certain amount of water which is going into the land. Then we have other cases like deflation, longshore sediment transport, sorting of beach sediment, etc. The man induced causes, this is land subsidence from removal of subsurface resources. So we have this heavy metals concentration on the sea coast, say they dredge the sand. Then the interruption of material in transport, that is construction of breakwater. Reduction of sediment supply to the littoral zone, I will explain littoral zone in one of the slides. So when there is a interruption of transport, one side it get deposited, that means whatever sediment it was carrying, that is in the littoral zone, that is depleted on the northern side, so that causes erosion. There are certain concentration on the wave energy on the beaches, if there is a concentration of energy, the erosion is more. The increase in water level is also a man induced cause because of the temperature increase, global warming and things like that. So we cannot say the increase in water level as natural, it is also man induced. Then removal of material from the beach, that is this is removal of beach means that is the dredged material. There are various methods that are used for coastal protection. One is called as the bulkhead, another is a seawall. Both bulkhead and seawalls are constructed parallel to the shoreline. Bulkheads, they are retaining the soil, whereas seawalls do not retain the soil. Both are designed to resist the wave attack. There are many materials that are used for building the bulkhead and seawall. They can be made of steel, timber, concrete piling, gabion boxes or rubble mount structures. So we will be discussing about the various types of seawalls, but we will concentrate on this rubble mount seawall with gabion boxes as toe protection in detail. Revetments, this on the beach itself we put some filter layer and then put some armor units, this is called as a revetment. So this revetments also is a energy dissipator, they have less adverse effect on the beach. We have one more concept that is called as offshore submerged breakwater. These offshore submerged breakwaters are built in the sea and they act as a wave energy barriers and protect the landform or water area. So let us see by sketch all the different types. Suppose you have a shoreline going like this and then this is your water level. Revetment means you put some structure on the slope, this is called as the revetment. Then when you talk about the offshore submerged breakwater, this is some kind of a structure which we built below the water level. So whenever the wave is travelling from the seaside to the land side, when it comes over here the wave will break here. So breaking wave height is, suppose this is your wave height h and this is your water depth d, h by d cannot be greater than 0.78. So instead of the wave breaking somewhere here, since we have reduced the water depth here, the wave will break here, that means the wave beyond this point will not have any energy, so it will not create any erosion. And about the seawall there is a separate sketch that I will discuss. Now this is only for revetment as well as for submerged breakwater. This is called as a submerged offshore breakwater. Suppose you want to protect some land area here, you build this breakwater. It can run into about a kilometer or depending on where you want to build. It can be detached also, it cannot be, it need not have to be continuous. Then we have the groins. These groins are barrier type structures, they extend from the back shore into the littoral zone. The littoral zone is the zone in which you will have the what is called as sediment transport taking place. So it depends on the point where the waves break. Normally when you talk about the waves will be different. During storm you will have very high waves, during normal period the waves will not be so high as a storm or cyclonic wave. But 90% or 95% of the time, what is the wave that is going to be attacking a shoreline, that you can find out statistically. Suppose that wave is about 1 meter, then the water depth it breaks will be the water depth in which the wave of 1 meter will break can be calculated, that is 1 divided by 0.78. So this will be approximately about 1.3 meter. So the distance from the shoreline to 1.3 where the water depth of 1.3 meter occurs, that is the zone where the littoral drift will be more. You find out that width of the distance, you take twice the width, that is called as the surf width. It is clear, no? Where the water depth is about 1.3 meter from the shoreline, it can be, generally the slope of the beach will be about 1:100. That means 1.3 meter water depth will be available at a distance of 130 meter. The beach slope is 1:100. So you take 260 meter is the zone where the littoral drift will be very critical. Suppose 90% of the time the wave height is 2 meter, then 2 divided by 0.78 it becomes 2.6 meter, and the slope is very flat 1:200, then you have to multiply by that and correspondingly your littoral zone will vary. So purpose is to modify the longshore movement of sand to either accumulate sand on the shore or retard sand losses. This is the purpose of the groins. This has to be done very systematically. Systematically means we have to carry out analysis and then decide. Groin is not built alone, we have what is called as a groin field, number of groins are built with certain sufficient gap, there are mathematical formulations for that, maybe about 10 to 12 groins will be filled, will be constructed, and this construction methodology also is important. There are 12 groins means you cannot start constructing the first groin, then second, then third, like that. Preferably you have to construct all the 12 groins, you have to start at the same time. Sometimes it is not possible, but at least 4 or 5 groins you have to start together, and the season in which you start the groin also is important, whether it to start on the southwest monsoon or northeast monsoon or non-monsoon, that is also important. Which is better, which season it is better to build the groin? I have listed 3 monsoon periods. Non-monsoon is the best because there is no little drift, so it is better to start on the non-monsoon. Non-monsoon I have written about 2 months, so it is preferable to finish in 2 months time. And these groins various configurations, these are also built using timber, steel, concrete or quarry stone, and they can also be classified as high groin or low groin depending on the top level of the groin, long groin or short groin depending on the length of the groin, permeable or impermeable depending whether if it is a quarry stone it is a permeable, if it is a solid concrete block caisson type of thing it is impermeable, and fixed or adjustable. We can have floating groins also, floating platforms can also be used as a groin, then it is adjustable. Then we have jetties, these are used at inlets to stabilize the position of the navigation channel, they are used to shield vessels from wave forces and control the movement of sand along adjacent beaches so as to minimize the movement of sand into the channel. Jetties are built mainly at the inlets. Then we have artificial nourishment. This artificial nourishment is done by the sand bypassing system. I told one side there is accumulation, another side there is a erosion. So take where it has accumulated, deposited, and put it on the place where it is eroding. It is a very simple principle, but it is costly, so you have to do that. If it is 1 million cubic meter, you are considering 1 million cubic meter of sand is to be deposited after dredging from the southern side and put it on the northern side. So this sand is in a sheltered pre-dredge deposition basin, it is the sand moves, the dredge material is normally pumped across the navigation channel to provide nourishment for the downdrift shore. Normally artificial nourishment what we do is we call a sand trap, that is built, especially on the east coast the sand trap is on the southern side where it gets deposited, then from the sand trap, that is you dredge the area more so that all the sand is collected at a particular place. Normally it is about 1000 meter by 1000 meter for a depth of about 10 meter. So 1000 meter by 1000 meter for a depth of 10 meter means it will be about 10 power 7 cubic meter. So you dredge from that and put it on the northern side. So the literal transport is by waves and currents, this is the movement of sedimentary material. So we have what is known as fall velocity, that is in this zone where there is sand movement, there are some sand particles which are suspended like this, and these particles we define by the fall velocity. It depends on the grain size, we call it as a D50 size, that is the size of the sand particle. Due to wave and current, if the velocity is more than the fall velocity, this will be suspended. The wave and current velocity is less than the fall velocity, this sediment will get deposited. Clear? No, due to wave and current you have a velocity, if that velocity is more, the sediments will be suspended or it will pick up some sediment from the shore causing erosion. If the wave and current velocity is less than the fall velocity, then the sediments will settle down. So the littoral zone extends from the shoreline to just beyond the seaward most breakers. I said already the breaker is that h by d is equal to 0.78, and we have different type of transport. One is called as the onshore offshore transport, that is from the offshore to the onshore. Another is the longshore transport, that is along the shoreline. This along the shoreline only is obstructed by breakwaters. So we have the transport. There are three directions. One direction is along the shore, another is perpendicular to the direction, perpendicular to the shore, the third one is the water depth. So these are the three directions. So you can have a onshore to offshore transport, just as I have shown in this sketch, onshore to offshore, or we can have a longshore transport. So this onshore offshore transport has an average net direction perpendicular to the shoreline. This is usually the most significant type of transport in the offshore zone, except in regions of strong tidal currents. And the longshore transport average net direction parallel to the shoreline. So parallel means it need not have to be exactly parallel, it can be slightly inclined also. Both transports are significant in the surf zone. Surf zone means twice the width of the breaker zone, that is what I discussed earlier. There it will be very significant. So we are going to study some case studies. We are going to study 6 locations, all of them are on the east coast, because west coast the littoral drift is not from south to north. Some places it is south to north and most of the places it is from north to south. This is because of the topography, because of the bathymetry and the direction of the waves. In Pondicherry fishing harbour, this shoreline is protected by various means, by sea walls, but what we have suggested is artificial nourishment. This artificial nourishment is a continuous process, we have to carry out every year. As I told, it should be done preferably in the non-monsoon season, starting from December 15th and complete before March 15th. They are not carrying out every year because of funds constraint, but when they have done it, this artificial nourishment, they have seen that it is making the shoreline stable on the northern side, preventing it from erosion. So for this artificial nourishment, we dredge in the harbour basin, and there is a submarine tunnel from the southern side to the northern side. That means you pump the sand below the seabed using a submarine tunnel, and you lay a pipeline on the onshore for about 3 kilometers and dispose the dredged material. So here you are seeing this photograph again. This is your south breakwater and this is your north breakwater, and between them you have a submarine tunnel. You dredge it here and then through the submarine tunnel it comes. You are able to see the pipeline here. Through the pipeline it comes and it deposits at all the places. What you are seeing here as a rubble mound seawall, it is also seen here, rubble mound seawall. These are all the places up to which the shoreline was there. Once we start pumping the sand inside the harbour basin and brought it here, the sand has deposited here and advanced the shoreline, and this rubble mound seawall is not required for any shore protection. The advantage is we have a very nice beach, the fishermen can beach their crafts here, people also can go over here. Here also you are seeing the 2 photographs where earlier all along the compound wall they have put a sea wall. The compound wall collapsed also 1 or 2 times, but now this is not required. This is a famous Gandhi statue in Pondicherry beach, where they have put the sea wall to protect, and waves were breaking on the sea wall, but now after we did the artificial nourishment we can see the beach formation here, people are enjoying the beach here. And another stretch where the sea wall, rubble mound sea wall was subjected to wave attack, after we have done the nourishment you can see the beach which has formed. The unfortunate thing is they have discontinued this artificial nourishment. Now we are seeing like this only, not like this. no beach in Pondicherry. This is very advantageous, this type of beach nourishment. The second is the sea wall, this is for shore protection. This is a one time construction cost, only marginal cost is required for maintenance. We have what is known as a rubble mound type sea wall. We have different components of the sea wall like core layer and armor layer. In Kerala coast most of the places they have done this rubble mound type sea wall. In 2000 when this sea wall is to be built in Kanyakumari district and Tuticorin and other places, we have introduced this geotextile filter and gabion box for toe protection, because most of the places when we do not use the geotextile filter and gabion box for toe protection, the sea wall fails during cyclonic condition. So this is an improvement which has been built into the design of the rubble mound sea wall. We will see the construction procedure of this rubble mound sea wall. There is a design procedure, I will not be discussing it here, but it can also be designed just like a breakwater. This shows the typical cross section of the rubble mound sea wall. We have given mean sea level as 0.0, this is not a normal convention. Chart datum is given as 0.00, but here we have used mean sea level as 0.00. So we can take about 30 centimeter below the mean sea level, we have to take. Typically the sea wall width is about 18 meters, that is from this point to this point is about 18 meter, and we give you a slope of 1:10. So if you give you a slope of 1:10 and 18 meter, the vertical elevation difference will be 18 divided by 10, that is 1.8 meter. So here we have minus 0.3 meter, that means here you will have plus 1.5 meter, right. So if tidal difference is larger, then the width has to be increased, so that this level is above the highest high water level. Here mean sea level is 0.0, in Kanyakumari district and other places the water level variation is, tidal variation is about 0.6 meter, right. That means this will be approximately your low tide level, and 0.3 meter above mean sea level will be your high tide level. So 0.6 meter is the tidal level, that means part of the breakwater will be submerged during high tide level, but there during low tide level there will not be any water, so it can facilitate construction. Point is clear now. From the shoreline when you want to build up to the low water level, you have certain duration in a day where it is without water, so you can do. We put a geotextile filter, this is to separate the seabed material with the base layer. Generally this base layer is a filter layer using sand. Then we have a core layer, this core layer consists of stones 50 kg to 125 kg. Then we have the armor layer which is 400 to 500 kg. This weight of individual stones 400 to 500 kg can be calculated based on the wave height prevailing at the particular location using Hudson's formula. Here we have two slopes, one slope is 1:10, another slope is 1:4, so that we go at plus 3.35. So even in a very big waves come, the wave will not overtop and come down, that is why we provide a steeper slope. If you provide the same slope, the top level will be much lower, so we provide a larger slope, and this is called as the gabion box provided at the toe. This is the toe of the breakwater. Here we put 1 meter by 1 meter by 1 meter box gabions. These are filled with the stones of size more than 150 mm, because the opening size for the gabion box is 100 millimeter by 100 millimeter. These gabion boxes are tied together adjacent box it is tied together, and there is a base Dobian box, 2 boxes are provided. So with this we will be tying this, and the geotextile filter is provided like this. We will see the advantage of geotextile filter as well as the Gabion box in the coming slides. The bottom we are providing 2 boxes, 2 numbers, 1 by 1 by 0.5, the height is 0.5, the aperture size and stone size is same, and aperture size, bigger size also you can provide 150 by 150 also depending on the wave height. So these are the components of the seawall. One is a geotextile filter, the other is a filter layer, the third one is a core layer, then armor layer, then Gabion boxes. So this is in a slope of 1:10 and about 5 meter towards the sea side and 13 meters towards the land side. The 5 meters towards the sea side is from the high tide level to the toe, that is about 5 meters. The filter layer consists of stones up to 150 mm of about 300 mm thick. I said this base layer or filter layer can be sand, it can be stone also up to 150 mm size, because at this location the base material itself is sand. Suppose you have a clay, then after putting a geotextile filter it is better to put a sand and then put a stone, depending on the subsoil condition the filter layer varies. Then we have a core layer. So this is the size of the stone and this is the thickness of the core layer. Normally if you use size of stone 150 mm, twice the size of the stone we have to put the thickness of the filter layer, at least twice the thickness of individual material should be there. Here if you are putting 500 mm thickness, the average size of this 50 kg to 125 kg stone will be 250 millimeter. Then armor layer is 1000 mm, this over a core layer of stones 400 kg to 500 kg, the approximate size will be about 400 millimeter or so. So twice the size we have to provide this. Then we have provided Gabion boxes, 2 sizes, 1 by 1 by 1 on top and 1 by 1 by 0.5 on bottom. You can put 1 by 1 by 1 also at the bottom, but since the core layer is 500 thick, we have used 500 mm Gabion box to retain the core layer, and since the armor layer is 1 meter thick, we have used a 1 meter thick Gabion box to protect the armor layer, right. Suppose the core layer thickness is more, you can go in for a bigger size also. What is the importance of geotextile? This geotextile is made up of polypropylene woven geotextile. Main function is to act as a filter media. Filter media means like our coffee filter only, between the existing bed profile and the bedding layer. Bedding layer is nothing but the filter layer. It allows the water to percolate, but it does not allow the seabed material to get into the bedding material. Bedding material is a filter material, either a sand or a stone of size up to 150 mm. So these two things should not come in contact. That means there is a permeability of the geotextile filter. It should be such a way that the pore size is smaller than the particle size of existing seabed material. So seabed material is 40 microns, the pore size should be 35 microns or 30 microns, so that this bed material will not go through that. This controls the cover and loss of bed material by the way of infiltration. These are the advantages of using geotextiles in shore protection works. One of the important parameter for the geotextile life is UV protection, UV resistance. This are woven together in such a manner so as to provide dimensional stability relative to each other. These geotextiles are normally coming in rolls, maybe in 3 meter width. So you lay one 3 meter width and put another 3 meter width with the overlap of about 300 millimeters, so that it can be stitched together. You cannot have, suppose you want to build a breakwater for 1 kilometer long, you cannot have 1 kilometer long geotextile. So 18 meter is the width of the rubble mount seawall. So for the roll can be of about 100 meter or something like that. So 3 meter you lay it, then cut it, then put another 3 meter with a overlap. There are 4 sketches shown here. The left side is the one without geotextile, top and bottom figure. The right side is with geotextile, top and bottom. The top figure is initial placement, both look alike, only thing is here we have a geotextile filter. The bottom after many wave cycles. So what you are seeing is this bed material is mixed with the stones which are coming here, whereas here you are seeing the bed material. Here we have not shown the bed material, but bed material exists here, but there is a filter fabric here, below that we have the seabed material. So this is the seabed material, this is the core material, this is the armor stone. So the seabed material and core material there is no filter fabric, so this material can go down, this material can go up. So whole thing get mixed here. The small stones and gravel separate and move away, and the large stone drop, these stones also will drop and they also will separate, then we will have a progressive cover and sand infiltration also will take place. This is the disadvantage, and over a period of time you see we have 2 layers of stone, some of the stones are not here, missing, it might have been taken away by the waves or it would have gone inside. So here we have the geotextile filter, it does not allow the seabed material to go inside, this does not allow this cover to take place. The small stones may, it is not like this, it is down but it remains there to protect the toe, but this alone is not sufficient. As you see here there is a potential failure at the toe, so here only we have provided the gabion boxes to further strengthen as a toe protection. So the gabion boxes, these are also made of polypropylene rope, they are having adequate UV stabilization. UV stabilization means they will provide some coloring is there, some black color, some tar coating or something like that they will do, but there are different type of gabion boxes, one is made of metallic wires, another is made of rope. We prefer rope because it is flexible and adjusts to the seabed. This acts as a toe mount of the seawall so as to avoid failure of the toe. The gabion boxes are flexible, they are not rigid, the metallic gabion boxes are rigid whereas these gabion boxes are flexible. They are collapsible type with a rope opening size of 100 mm by 100 mm. Collapsible means for packing and all it is very easy, so it is collapsible, just you have to open it up. Over a period of time the gabion boxes attain a stable slope and thereby prevent the dragging of the stones into the sea. So it may get submerged, it may not be remaining vertical, it may change its shape, but it will remain there where you have placed. So it will protect the stones, the core stones and the armor stones to slide into the sea. How to do this construction? Another 5 slides we will show how the construction is there. Here we are seeing the seabed. So here what you are seeing is the roll of the geotextile fabric. You lay it here and then put some sandbags of about 300 mm thickness at intervals of maybe 2 meter or 3 meter. This is the sea side and this is the land side. Next you place the filter layer, that is 150 mm thickness, up to 150 mm size, 300 mm thickness, you maintain the slope of 1:10. Suppose the slope is flatter than this, you may rise it to make it 1:10. If it is steeper also, if it is steeper you fill it and rise it, if it is flatter you make it as it is, you do not make it slope 1:10. Suppose it is 1:20 slope is there, you leave it as it is, do not try to make it 1:10, but you adjust in the core layer. Then we place the gabion box of 0.5 meter height, then next you put the core stone, next you place the another gabion box, next you place the armor stones, and this geotextile filter you can take it down inside like this before placing this toe mount gabion box, you can take it here like this. This you can take it back like this so that it can be anchored, you can take it like this and take it like this also. This here you see the houses here, they are very close to the shoreline, they have made some concrete wall here, there are some fishermen boats are here. Now what they want to make is this looks to be flatter than 1:10, they are trying to make some slope what we have designed, and then they have laid the geotextile filter. I was telling about 3 meter, this is the 3 meter width, and then they will put another 3 meter here, they will overlap here 300 millimeter. This is the seaside, whatever sand they are excavating here they put it as a cofferdam here, they have put the gabion boxes. Originally we have taken the filter fabric on top of the gabion box, finally we found that it is not good, it is not as good in ultraviolet protection as before and does not allow the dissipation of waves also, it gets damaged very easily. The best way is to take it below the gabion box, that is what we did earlier. This is the core stone which they are filling it up here, then this is the gabion box, afterwards we removed this filter layer, and you can see a person where height may be about 1.7 meter, this height will be about a meter. These are collapsible type, this is called as the aperture size which is about 100 mm by 100 mm. You are filling inside with stone, the size of the stone should be greater than 150 millimeters. There are certain specifications, geotextile woven fabric, there are some 26 by 130, these are some the 26 is nothing but some strength which it should have, weft strength in kilonewton per meter which is 26, that is mentioned here. Weft and warp are two direction, where we are doing the woven geotextile there are two directions, one direction is called as warp, another direction is called as weft. In the direction of the woven direction it will be more, otherwise it will be less. This 130 is grams per square meter, that is if we take 1 square meter of this geotextile filter and find the weight, it will be about 26 grams per square meter. So if you want higher strength, V1 up to 80 we can have, weight can go up to 360, 380 grams per square meter. Then we have some elongation at which it will fail, then some grab strength and trapezoidal shear and the hydraulic pore size 0.075 and less. What is the permeability? These are all to be decided based on your seabed material, the size of the pores of the geotextile fabric. This is for the gabion box, this weight is 45 grams per meter. This is a polypropylene rope, the breaking strength is given, mesh opening size is given, punching shear strength, the type of the rope, abrasion resistance, thermal stability, resistance to UV radiation. Normally they claim it is resistant for about 10 years, 15 years, 20 years like that. Actually it will not fail, maybe the strength will reduce by about 40% over a period of time. What are the functions of various materials we have used? One is the geotextiles, they perform the functions of filtering. Filtering means allowing the water passage. Separation between the seabed material and the filter material. It acts also like a reinforcement when used in shore protection. If you put a geotextile filter, the whole mass above the geotextile filter act as a single unit. This is a polypropylene multi-filament woven fabric, the individual multi-filaments are woven together so that it provides a dimensional stability relative to each other, and that is why we suggested this as a filtering media. Earlier days what they use sand itself as a filter media, where we have a clay bed we use sand itself as a filter media, but this is a better material. The cost is not very high, maybe it may be around 100 rupees per square meter now. Then we have the gabion box. The cost of 1 meter by 1 meter by 1 meter box will be around 1500 rupees, and this is the size of the opening, 100 by 100 filled with a stone of not less than 150. Then another size is 1 by 1 by 0.5. So with this we have completed the second case study. First case study is artificial nourishment, second case study is the sea wall. The third case study what we are going to see is for Gopalpur Port. There we will be seeing three types of shore protection. The three types of shore protection that will be considered are, we will have groins, we will have a sea wall, we will also have artificial nourishment. So all the three we will be doing. This port is under construction now. They have completed the groin construction, they partially completed. Artificial nourishment they are going to do shortly. This is in the east coast between Andhra and Orissa border in the Orissa state. So this is the southern breakwater, it is about 2.5 km long. Now they are building this intermediate breakwater, it is called as a north breakwater. Already there is a coastal inlet inside, they have two breakwaters here, and these are the groins which are schematically shown, but detailed design has been carried out recently. And this is your 5 meter contour, this is your 10 meter contour, this is about 15 meter contour. This 10 meter contour is available at a distance of about 700 meters or so. It is a very steep slope, the ideal location for a port development. So if you go about 700-800 meters, if you get 10 meter contour, it is really good. Most of the other places it is varying from Tuticorin, it may be 10 meter contour may be available after 3 kilometers, Chennai 1.5 kilometers, here it is only 700 meters. This is your existing shoreline. After development we want to, this when you start building this breakwater, the shoreline also will advance like this, and this is the sand trap which will be created 1 kilometer by 1 kilometer for about 10 meter depth. So when there is a nourishment, when there is a deposition taking place, so it will get deposited, original water depth will be increased in the sand trap by about 5 to 6 meters. So the sand will get deposited here, the dredger will come and remove the sand, and then they will go here and they will nourish the beach on the northern side using now we have what is known as rainbow technique. I have a slide, I will show that. At present what they are doing is they are making this navigation channel and the training basin. The first phase is under construction now. When they do this dredging, there are two types of dredging. One is called as capital dredging, another is called as maintenance dredging. So in the maintenance dredging they will maintain the channel, they will remove the material from the sand trap, these are the things they do it. Generally this maintenance dredging will be about 5 to 10% of capital dredging. I think capital dredging they want to do about 8.5 million cubic meter. So maintenance dredging will be 10% of this, means 0.85 million cubic meter. So every year they have to remove 0.85 million cubic meter and deposit on the northern side to make this shoreline stable. So these are showing some cost. The cost of the project is about 11,203 million rupees, out of which about 10% they have provided for environment and pollution control. The operating and not 10%, it is coming about a percent, 1%, right, about 1%. Operation maintenance cost is about 10%. Then these are the O&M cost for environmental pollution control measure, that is every year they will be spending about 3.96 million cubic meter, and they will complete the total project in about 36 months time. It takes about 3 years to make the port operational, phase 1 and phase 2. Phase 1 they are planning to do in 18 months. What are the environmental concerns? This is what I started in the beginning. When you want to build a breakwater, there will be certain issues in the environment. What are these issues? One is the construction of the breakwater will lead to obstruction of littoral drift. The major annual drift will be about 1.333 million cubic meter annum northwards. There will be a southern drift also, but northern drift is about 1.333 million cubic meter per annum. Estimated accretion is about 140 meter per annum at the root of the south breakwater. That is, when you have the south breakwater, the shoreline would advance by about 140 meter every year if we do not do any protection measures. Estimated erosion is 20 meter per annum at 2 km from north of the breakwater. Suppose you have the north breakwater here, at 2 km away from this it will erode by 20 meter. So this accretion will be like this. So accretion will go like this. At the root of the breakwater it is 140 meter. As you go towards the southern side it will get reduced. Similarly erosion may be more here, but as you go about 2 km the erosion is about 20 meter per annum. This is based on the numerical model study, and this is happening also. We have seen that after construction of breakwater, this much accretion on the southern side and this much erosion on the northern side. What is the mitigation measure? We have to, for capital dredging, to create the entrance channel. See this channel, I have seen this is 5 meter, 10 meter and 15 meter contour. The channel depth should be 15 meter, that means the whole area here they will dredge to 15 meter. Whatever material that they are dredging, some of them will be disposed into the sea, some of them will be put on the northern side. So that is about 5 million cubic meter they will be stockpiled on the northern side as an advance action for north shoreline protection. This is an advance action. So we make a stockpile means we put more sand than it will get eroded, so that for another 5-10 years you do not have to do any artificial nourishment. So we make a stockpile, but the stockpile will remain in place if you do a groins. We have a groin field along with the artificial nourishment, then even for about 25-30 years we may not have to do any artificial nourishment. We have to see what happens with the groins. And the maintenance dredge material, which is about 5% or 10% of the capital dredging, they also will be discharged on the northern side for nourishment against erosion using rainbow technique. This is the mitigation measure. Whenever you submit a environmental management plan, you have to give two parts. One is what is the impact and what is the mitigation measure, and you have to enforce the mitigation measure. So when you want to construct the breakwater, southern breakwater is about 2 km, north breakwater is about 500 meters. The stones required are about I think this 3 million tons with artificial armor. Now it has gone up to about 6 million tons with a berm breakwater. When you dump the stones, they will disturb the sea bottom and benthic flora and fauna. Current at the tip of the breakwater shall be higher, causing difficulty for navigating small country boat. These are all the impact. The mitigation is dumping shall be carried out mostly from the land by using proper hoisting equipments. Then the recolonization of the benthic and flora will take place immediately, and we should not use any explosives or anything like that at this location. If this is mainly if you want to make a trench and things like that, and you have to make marker buoys for safe navigation from the tip of the breakwater. You should mark some distance so that they know where the tip of the breakwater exists. Then we have one more item, that is what is the effect of dredging. There I am discussing about 3 issues. One is what happens to the shoreline, what is to be done when you build the breakwater and what is to be done when you do your dredging. The dredging volume is about 8.5 million cubic meter, 5 million cubic meter is sent to the northern side, 3.5 million cubic meter at about 25 meter water depth. This dredging and disposal they also will disturb and it will also create some turbidity. So, a mitigation measure is there will be limited temporary dislocation of sea bottom flora and fauna in the harbour as well as the approach channel during construction period. The recolonization will start soon after the completion of dredging. This can be done by marine EIA studies. What you have to do is you have to carry out a monthly study to ascertain what is the parameters. Before starting the work we should collect the data and that you use it for comparison with the data when you do various activities. This control you have to do for dredging and disposal by using latest technology, putting silt curtain limiting the area of turbidity, and if the material is sand the turbidity will be less, if it is a clayey material the turbidity will be more. Mostly in Gopalpur it is a sand material, so the turbidity will not be a problem also. And when you are depositing in a 25 meter water depth, when you are depositing 8.5 million cubic meter over an area of about 3 kilometer by 3 kilometer, the bed level shall not increase more than 1 foot, that is 0.3 meter, because we are removing the soil and we are putting at 25 meter contour, the water depth shall not vary too much. So that also you have to see. And to keep the artificial nourished sand in place we are planning about 9 groins. Now we have increased it to 11 and about 5 million cubic meter will be nourished on the northern side as a stockpile, and further when you do the maintenance dredging we will use it by rainbow technique to the northern side. This shows the photograph of the groins on the northern side. This shows your southern breakwater and the intermediate breakwater. This is the groin field which is on the northern side. So you can see here the groins, this is called as a transition groin. The length of the groin typically reduces as you go towards the north and the spacing between the groin is proportional to the length of the groin. Typically the spacing between the groin is about 2 to 4 times the length of the groin, but you have to do some model study. So over a period of time shoreline after 25 years the shoreline advances like this. So actually this has happened in Chennai port. I will show the satellite imagery how the shoreline is advancing. Generally the shoreline is advancing on the southern side and the seawall is built beyond this last groin, right. We have the groins and we have the seawall. This artificial nourishment as a stockpile, what we will do is we will fill up to this point originally itself. So this whatever we have filled it may get removed over a period of time. Ennur port we have done the stockpiling, I will show the photograph how we have done that. The groin cross section is shown here. So we have the seabed at about the tip of the groin varies at different contours, it may vary from 1 meter to 4 meter. At about 3 meter water depth if you want to put the groin we have to put the top layer. The width of the groin is 4 meter for construction purpose. Armor layer is bigger size stone 1000 to 2000 kg, then we have a secondary layer 100 to 200 kg, then we have the core layer 1 to 50 kg, then we have a filter layer 10 mm to 50 kg, then we have the toe mound here which is about 100 to 300 kg. So this toe width is 3 meters, depth is about a meter and the slope on both the sides are about 1.5 horizontal to 1 vertical. The top level is 4.2, the highest water level is somewhere around plus 2.2 or so, we are keeping it much above this 4.2 meters. This shows the CRZ map. The CRZ map in this case has been made by National Institute of Oceanography. There are only few agencies which are authorized to make this, 7 agencies, one of them is NIO. They are marking various coastal features, they are putting the groins also, they are putting the sand trap, entrance channel and the turning circle. This is the first phase, this will be the second phase. This is the groin which is built for the inlet, these are the 9 groins, beyond that we will have the sand trap. This is what is actually now being built now, these are the inlet groins, these are the 11 groins, the distances are shown here, this is the seawall which is shown here. These groins are built 50% now. Now they will be stockpiling the sand right up to this toe of the breakwater. Normally they use a dredger to dredge the basin and there is a pipeline here. Initially what they want to do is they want to nourish the portion between this existing breakwater for the inlet and the first groin by laying a pipeline. Other thing they will go into the sea here by another dredger and then do a rainbow. I will have a slide, I will show that. So they are dredging and there is a floating pipeline. The floating pipeline will go, they will take it to the shore. They are dredging here, the pipeline will go like this and go here like this, it will cross and it will cross like this and it will get here deposit. These are the 2 groins for the inlet. There is an approach trestle earlier and this is the first groin. So the floating pipeline and the pipeline on the land will nourish the distance between the first groin, northernmost groin of the inlet and the groin number 1. This is earlier built to make this mouth opening. So this is the pipeline which is being laid for one of the project for reclamation purpose, same thing they can use. This slide shows the groins built and the red line shows the shoreline when the groins have been started, that is in December 2011 this was the shoreline. Now December 2012 this is our shoreline, about 20 to 40 meters the shoreline has got eroded. This is what we predicted, about 20 meter will get eroded as we start constructing our groins. So this figure is clear, this is the shoreline in December 2011 when we started the construction of breakwater and construction of groins. Over a period of time the erosion has taken place like this. Now we are doing the artificial nourishment and bringing this shoreline green line to this level, tip of the groin. This is called as a rainbow method. So what they do is from the dredger they put it on another vessel or the same dredger will come here, then they pump it like this, about 300 meters it can go and then pump and then it will stockpile. So groin number 2 to 11 they will be doing this rainbow technique. So here groins are there, sea walls are there, artificial nourishment by pipeline as well as by rainbow technique. Then some of the material what they are dredging here they will be taking it to a place somewhere here for dumping between 25 meter and 30 meter contour. So part of them will be going by pipeline between these 2 points, part of them will be going by rainbow technique from this point to this point. This is the sand trap and entrance channel where they will do some maintenance dredging and put it on the northern side. So this is the dispersion of the dredge material which is put in 25 meter water depth, how much depth it is increasing, that is what is shown here. For various tide we can do a numerical model and we have shown the locations where this dredge material will be dumped. So 2 million cubic meter will be disposed on the north side of the existing channel which is nearly 8 kilometers from the center of harbour basin, and the balance we have to dispose it off into the sea. This deposit is about 25 meter CD, the coordinates also are given. So now this estimate has been revised, about 5 million cubic meter will be disposed to the north side and 3.5 million cubic meter will be disposed to these locations. This slide shows 2 ports near Chennai, this is your Chennai port, this is your Ennur port. You are able to see this accumulation on the southern side, right, this is taking place and this is your fishing harbour and you have a very good marina page on the southern side of it which I am not showing it here. There are series of groins built before the tsunami in 2004 which has saved a lot of life and property all along this shoreline. This next Google map will show the groins. You are able to see the groins, right? These are all the groins which are built. Earlier this is the road, what you are seeing is the road earlier, now also the same road. Only thing is earlier the shoreline was all along this road, now the shoreline has advanced. Earlier our shoreline was along this road, sea has penetrated inside. What happened is originally the road was here, then it has eroded the road, then they shifted the road inwards, then it has eroded that road also, then they have shifted the road, like that they are going on shifting the road. Now after construction of the groin, the shoreline has advanced, they do not have to repair the road or rebuild the road, that is an advantage, and they are getting a lot of land also here. The cost of the land is much more than whatever the money we have spent. Which is the northern side for this breakwater, for the groin? This is the northern side, this is the southern side. It is very strange that here northern side we have the deposition for this groin, and southern side we have the deposition for this groin. Depends on the season, which season you are taking the photograph. If you are doing it in the northeast monsoon, your deposition will be on the northern side. If you are doing it in the southwest monsoon, your deposition on the southern side. How much it has deposited, how much it is eroded, based on that your final shoreline will see. You see the next slide, one of the groin here you have the deposition on both the sides, whereas this groin you have the deposition only on the southern side, some more deposition on the southern side and less on the northern side. So it depends on where it is, what is the spacing between the groins, what is the depth at which it is going, what is the bathymetry, all these things decide how much. When the tsunami has come, most of the deposition has been taken away by the tsunami, but within a period of 5 to 6 months the shoreline has advanced after the tsunami. In Ennur port we have made a stockpiling of an artificial nourishment using the capital dredge that is shown here. So this is the Ennur breakwater, northern breakwater, southern breakwater, and as they have started construction of this breakwater, the shoreline has advanced maybe about 500 meters, and whatever material they used to create the basin they put it on the stockpile on the northern side. This is a natural deposition, this is artificial nourishment as a stockpile. Now this stockpile has got is getting eroded, as you see here some portion has got eroded, and then they have to do the maintenance dredging of this. This photograph shows the Visakhapatnam port. So this is the southern breakwater, this is a famous Ramakrishna beach. So one of the advantage of this particular structure is this breakwater is not starting from the shore, there is a gap between the shoreline and the breakwater, so that the sand will deposit here. They have created the sand trap inside, so that the dredger can come and work in calm environment to remove the sand, that is the advantage of this. But nowadays they are not doing this shore disconnected because it is very expensive. One of the first slide what I have shown in this lecture is your Pondicherry fishing harbour. Actually this is your southern breakwater, they did not start from the shore, they have put an approach bridge, then they started, but they did not dredge inside for artificial nourishment in the sand trap, that is why the whole bridge has got closed and the shoreline also has got advanced. So this coastal erosion typically on the northern side and accretion on the southern side is to be studied carefully, and the erosion should be avoided on the northern side. The three methods which are normally used nowadays are artificial nourishment as a stockpile, as a maintenance dredging. The second one is to build the groins while doing the stockpile. Ennur port we did not do that, in Gopalpur port we are putting a groin field, transition groins, at the end of the groin you put a seawall. So these are the three methods that are used to mitigate the impact of breakwater on the shoreline. Okay, thank you.